Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 32, and this question asks us to relate each of these compounds, A, B, C, and D, to A, and choose if they're either tautomers, constitutional isomers, or neither. So what a tautomer is, as from the previous examples, we have an alcohol that's bounded to a carbon that is also bounded to a double bond, and through some movement of electrons, we get a ketotautomer, which is far more stable at equilibrium. And as you see here, the lone pair electron of oxygen goes down to make a carbonyl bond. And when you make a bond, you break a bond. So then this alkene double bond goes to pick up this proton to neutralize oxygen to make sure it still has two bonds. So to determine if it's going to be a tautomer, we know that, so we have the keto form in A, so we know that the enol form should have alcohols in the position of these carbonyls, and these alcohols should be directly bounded to a double bond, either here, 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 or here. It's directly bounded to a double bond. So let's see if we have anything that matches what we have for determining if it's tautomer. So let's look at A. So for A, we have the original carbonyl here, but here we have the alcohol, and yes, in fact, we have this double bond here. So yes, this will be considered a tautomer because if we push those electrons down, we would get back the structure A. So A and A are tautomers. Now let's look at B and A. So yes, we have this alcohol, but the double bond is not directly attached to the carbon that's attached to the alcohol. So these are not tautomers. So what can it be? Well, we have constitutional isomer or neither. So constitutional isomers are two molecules that have the same chemical formula, so same number of atoms of oxygen, carbon, hydrogens, but they differ in bonding. So if we see here, we have the same chemical formula, we can determine that. And then this pi bond that's an A got moved over here. So we don't add any new atoms, we don't add any new molecules or any new elements or functional groups to this structure B. We have the same chemical formula, but just the binding and the bonding of this structure changes from A. So this is what we call a constitutional isomer. And now if we look at C, well, this is the same thing. If this was going to be a tautomer, then we would expect a double bond either here or here, but that's not the case. But this double bond that used to be on A here, this carbonyl bond, got moved over here. So it has the same chemical formula, but different binding. So this is also a constitutional isomer. Now let's look at D. Well, let's count our carbons for A. 1, 2, 3, 4, 5, 6. D has 1, 2, 3, 4, 5, 6, 7. So we actually gained a carbon. So a constitutional isomer, if you guys remember, has the same chemical formula. Well, D has one extra carbon than A. So this D cannot be a constitutional isomer, nor is it a tautomer of A, because tautomer only differs in their binding. So remember, yes, it is true that we have a carbon that's bound to an alkene with an alcohol, but we have an extra carbon here. So this structure is not the tautomer of this. This is a whole new, unique structure right here. So this is neither.